Good morning, ladies and gentlemen. I want to welcome you today to our webinar, CANape and MATLAB Simulink, the perfect team for model-based software development. My name is Stefan Herzog, and I'm a product expert for the product of CANape, and I'm doing today with my colleague together this webinar. So maybe you can say some words by yourself.
Good morning, everybody. Good afternoon. My name is Gernot König. I'm from the department Measurement and Calibration. I'm working on all CANape topics, doing customer projects and second-level support. And I will guide you through the demos today.
Okay, so before we start, first some technical issues. So if you have some technical problems, so maybe you cannot hear me now or you cannot see our screen we are sharing at the moment, so please use the chat functionality. So we try to fix this as soon as possible for you that you can join this webinar. If the problems are ongoing, so no problem, so because you will get a link after this webinar with some or an email with some information about this webinar, inclusive a link to a record of this webinar, so you can watch this webinar later if you want additional. This is no problem. If you have some questions to the content of the webinar, so please use the Q&A functionality of WebEx. So we try to answer your questions at the end of the webinar. So we're doing just now the webinar, and after the webinar is finished, we will answer then your questions. Okay, let's start the webinar, the perfect team for model-based software development. So just a fast view of on our agenda we have today. So we will start with a very quick motivation why we do this and why is it maybe a perfect team, CANape and MATLAB Simulink. After this, we try to show you in some theoretical and big practical parts the different topics. So we will start with the CANape option Simulink XCP Server. After this, we will have a look on the CANape vSignalyzer Target, and we will finish this presentation with the topic bypassing. These are now 3 topics, and we try to give you some backgrounds to these topics in the next, I think 50 minutes. And at the end, we will have then a quick summary. Okay, so first the question, why we can say CANape and MATLAB Simulink are a perfect team. So if we have first a look on the left side for MATLAB Simulink, so for what is MATLAB Simulink well known? MATLAB Simulink is a tool for handling big and complex models. We can create models for from the scratch. We can create code out of these models later for different target platforms and so on. So it's completely different to CANape. And what we are doing function development. That means rapid prototyping. We are doing after this for simulations. Sorry, let's do it again. So we can do simulations, and with simulations we can do things very faster than in reality. So especially in the ADAS area, this is the next point. The image processing maybe is very helpful in this area. So we have more and more things to test, and we have to do more and more driving kilometers. And so before we go on the road, it's always better to do these tests on models. We have faster calculation times. We have always the same environment. We have more computing power, and we can use always the same input values to compare then the different models during the development phase. Okay, and on the other side, we have CANape. CANape is well known as a ECU calibration and measurement tool. So what we are doing with this, we are handling parameters. We can set parameters in the ECU. So while we're doing this, so we have a software running on the ECU, and now we want to set up this software for different use cases. So maybe we have a target market for the US, we have a target market for Asia, and we have a target market for Europe. And so now we have to set different parameter sets so to have a different behavior of our ECU. And that's the reason why we must set and calibrate different parameters. And for this is a big advantage to visualize internal parameters or signals in our tool. Additionally, we have the possibility to do some data recording, so that means we can record data, all the signals we are measuring, we can record all the parameters we are measuring, and this not only from one ECU, we can do this from multiple sources. And CANape is a tool which supports many standards, and this is very important. So in this area, and additional with CANape, you can have a high-end access to ECUs. This high-end access is time synchronous, and we have extreme high data rates that are possible. We have 50 or 70 or more megabit per second to exchange data between the ECU and CANape, and this is important especially in the high-end area for ADAS functionalities. Okay, these are the two tools, and now the question, is this a perfect team for model-based software development? Yes or no? We try to give you an answer in the next minutes. So we start with the first topic, the CANape optimum Simulink XCP Server. This is the step one in the software development phase. This means a model in the loop phase. It's an early model development phase in MATLAB Simulink. We define models from the scratch. We have at the moment no target platform. The model is running on your PC. The functions of this application are tested normally in an iterative process. The model is only executed in Simulink, nothing else. Nothing else. And additional, we have in this early phase necessary to do an initial parameter settings. And how to do this? So we have in our tools in CANape and solution to do this. So we can make it happen that you can use CANape for do a calibration process during this model development phase. The model is running in Simulink, and CANape can be used as a familiar GUI for these models which are running in Simulink. We can visualize internal signals of this model in CANape, and we can set different parameters, like we can do it later in the real ECU. The model is completely remote accessed by CANape. That means we are starting CANape, and CANape starts the model running in Simulink later. It's nothing else than we are placing an XCP server, like we are doing normally in a standard ECU, in our model. And now we have full access to different functionalities of this model. So that's just the theoretical part, but I think we can show this very good in a practical part. And so let's switch to my colleague, and he can show you examples of this.
Okay. Hello, everyone, again. I would like to show you this now in a demonstration. And before I jump into the demonstration, I want to show you what I'm going to show you in the demonstration in a little animation here. So as you can see on the top left side, here's the model, and I use a model which comes with Simulink by default. It's called SLDemo Autotrans model. So we adapted it a little bit with new pictures, but in general, it's the model from provided by MathWorks. So this is a nice model because it shows automatic transmission, and it shows also some inputs. Here's a throttle and here's a brake. These are the inputs. They are generated by the signal builder block. They go into the model, and we have three outputs: engine RPM, vehicle speed, and gear. So this is the model we are going to show for the next three demos. And you can see the steps from the first step, from the mill to sill, and then to bypassing, all based on the same model. So what my colleague Stefan already explained is we have a vector XCP server block which needs to be added to the model. So that's done in here, and that's all you need to do for this step. There's only some configuration steps and some file generation steps now, which I explained in the demo. But then, with this block enabled, you or integrated in your model on the root level, you are able to measure and calibrate the data from the model, and you can work in Simulink time, not real time, but in Simulink time. But let's do this in MATLAB Simulink here. So I switch to MATLAB Simulink. I start the model, so the same model as you have seen in the presentation. Let's do a little simulation in here. You see that the plot here with the three signals is shown in here. So MathWorks has a plot, you know that, a block which plots all the signals. But we are sure that CANape can help you having better analysis of the data you get in MATLAB Simulink. And how to do that? Here's the thing. So we go into the Simulink library browser, and then you switch. Here's a separate icon or a section for the Simulink XCP server, and here's the block. So all I need to do is drag and drop this block to the model. So this model is now, or this block is added to the model, and with a double click you can change and configure the Simulink XCP server block. So let's a very first thing you need to do is start the server. From this moment on, the model is able to access via XCP. Okay, and the next step is, by the way, here go back to settings. As you can see here, there's a host name. So my model and my MATLAB is now on the same machine, but MATLAB can also run on a different machine. So I can add a IP address here and a port how this MATLAB PC can be accessed. Okay, so next thing is the files. So as you can see in here, we can generate a CANape project out of Simulink, which is nice because we don't have to do any setup later on in CANape. It's just a project you can use out of the box here. And there's a model description file. I will explain that later, what it does. And here's the SF2 export because we generate an A12 file. And here you can say what has to be exported to the A12 file. For sure, we have parameters. So in this case, all the parameters, and we have signals. And let's say all named signals. So everything what is inside of this model can be then accessed by CANape. Okay, that's all. I will switch to a different version because this is not a released version yet. So I'll switch to the released version, which is CANape 16 Service Pack 1, and select the CANape exe file. That's all. Apply, and then I generate the files. So, okay, it says create a folder for this. So CANape now creates all the files which are needed, and that's it. files generation completed, we are ready to go. And from within this block, you can start CANape right away. So that's a nice thing, and it also connects to the model. So let's start CANape. So I start CANape now, and we should see the same plot results as we have seen in Simulink. That's the goal. So here's my project. So I have a device here, which is my Simulink model, and I have all the signals which are accessible here. So in my plot, let's go back to the plot. There's gear, engine RPM, and vehicle speed. So I want to use the same one here. So let's see, where's gear? Oh, we can search for it. So let's use gear. Put it in a graphic window. Engine RPM. This was here. And I use vehicle speed. So you can see all the signals, all the model internal signals are available here, as you know it already, when you're working with real ECUs. So there's no difference to that, except for the timing. So when you now start the simulation, so we start a simulation, we start a measurement, but in the background, the simulation is started for this model in MATLAB. So we start the simulation. Let's run the simulation. It should run very fast, as you can see. This was 30 seconds. 30 seconds of time. So when I fit them on top of each other, you have exactly the same look and feel as you see in the plot. And then you can start analyzing this data with all the tools. And CANape has a lot of analysis tools, as you might know already, to analyze the data, because we record all the data, we create MDF files as general MDF files we generate also with real ECUs, and you can analyze the data. You can rerun the simulation and anything like this. So that's a great thing. And in addition, let's create a new page. And in addition, you can also create the model view, which is really nice, because you as a MATLAB Simulink developer or function algorithm designer, you want to see the view of MATLAB Simulink also in CANape. And this can be done with this Model Explorer. And as you can see, it's the same look and feel. You can go into the subsystems. You can even, here's a Simulink chart. Even the charts can be displayed, or the single states can be displayed here for the gears, for example. But also, which is also very nice. Let's make this not so big. But if I go into this engine block, here is a map or an array defined. So I can right-click on it, and it's called emap. It's also in the workspace. That's the workspace parameters. So I can create a map curve window, and as you can see, these are the values from the workspace, which are in the workspace, and you don't have to go back to MathWorks or MATLAB, Simulink, and change these values. You can change them right here, and then run the simulation again, and see the different behavior of your change here. So we create a new MDF file. We put them on top of each other, and then you can also, in the next step, compare them to each other. So very nice solution if you're working in a Simulink environment only thing. Next part would be what my colleague will introduce you, will be working in a real-time environment with real data. So I will give you the ball and talk to you later.
Okay. So just let me give you a very fast summary about the last step. So what are the advantages of this technology? So we can do optimizations in a very early development phase without real hardware available at the moment. We have completely full access to signals or parameters, and we can use the complete CANape environment like graphic windows you have seen in the demo before. And you are working in the same tool like you do it later in the development process. Later you will have CANape connected to the real ECU, and you can use the same projects like you used in this early development phase later too. Just do some little steps, but it's all possible very easy. And how to use the Simulink XCP server you have already seen in the demonstration, so I think it's not necessary to go through these topics step by step. Okay, the next block is the CANape vSignalyzer target. What's this? So we're coming to the step 2 of the software development, the software in the loop or first rapid prototyping. So we try to add now real-time data as a source maybe to our model. So the model is nearly complete developed, and we want to do some tests with real data. We connect maybe the model to an ECU, and we measure out of this ECU the real input signals of the model and connect this to our model. And in this early phase, the model is executed then on our PC, and for this we can create a DLL out of this model. And the parameter calibration is done with a real ECU environment then. How we do this? So CANape or with vSignalyzer, you can, or with CANape and vSignalyzer, you can create out of MATLAB Simulink a CANape vSignalyzer target. For this you only need a Simulink coder, and the file you will get out there is then a MATLAB, is then a Windows DLL, and this DLL can be directly used then in CANape. We can visualize and cascade these DLLs. For visualization, we have a special new window. It's called the Algorithm Designer in CANape. That means we have on the left side our Simulink model. We create out with the Simulink coder and the CANape or vSignalyzer target a DLL. Additional to this DLL, we'll get some more information like the A2L or the linker map file, which are necessary to use these files then later in CANape. And additional, we will get the model description files like you have seen before in the demo from my colleague to visualize this model then in CANape. So how to do this? We will see in the next live demonstration, and so I will switch to my colleague. Oh, so no, one additional point I want to show you. So one good thing is if the DLL is created, an XCP driver will be placed inside of this DLL. So we can use this directly like a real ECU, and it's not necessary to put in this XCP driver manually, like you have to do this in a real ECU. Okay, now switch to the model.
Okay, let's do the next live demonstration here. And as you can see, we use exactly the same model here for our CANape vSignalyzer target. By the way, this is one target. We can use this target or the DLL, which is generated in CANape in an online and offline use case, and also in vSignalyzer with only an offline use case, because vSignalyzer is an offline analysis tool. Okay, so for this target and for generating this DLL, there's some prep work to be done. with the model. And I will show this in this small animation here, and then later on in the tool as well. But just to visualize what I'm gonna do in the next couple minutes. Okay, so first thing is we have some inputs and output blocks. So you saw already the Simulink XCP Server block. So with our target, CANape and vSignalyzer target, we have different blocks, and these inputs and outputs, they need to be added to your model. This enables you later on in CANape to add these or use these blocks with any kind of signals or data sources you have in CANape. So you don't have to think about, in this stage, about, oh, what signal needs to go into my model. You can just define it as a placeholder, and later on in CANape, the configuration or the link is done in CANape. So we do this for the inputs, and we have two inputs, throttle and brake, but we do this also for the outputs, engine RPM, gear, and vehicle speed. So this is done here. And by the way, if you are thinking of, oh, I have hundreds of inputs and hundreds of outputs, we have also a solution for this to generate these inputs and outputs automatically. Okay, so next step would be creating this DLL. What Stefan already told you. We need to create a DLL which has an XCP driver included and all the other files which are mentioned already. So these files go into CANape, and then with these files, we are able, for example, in this demonstration, I have an evaluation ECU. As you can see down here, it's a vector ECU, and it's mounted on a board which enables the user to change inputs, analog inputs, digital inputs. So there are some switches here, and there are some sliders. So I want to use these sliders. The two sliders here on the left for my throttle and my brake signal. Okay, and the connection here is done with CAN, but it can be also with others. But this ECU provides a CAN access here. So let's do this in the demonstration. So I switch to MATLAB back. So where's my MATLAB? Where's my Simulink model? Oops, sorry for that. Here's my Simulink model. So I get rid of the XCP server block here. So, and as I said, I need to exchange these inputs and outputs by our block set. So let's delete this one, open the library browser again, and here under CANape vSignalyzer target, we have CANape IOs. As you can see, there are more than inputs and outputs. This I can explain in when you have questions about them or when you have the need to know. So let's look at the blocks here. So I use, so this is some work I have to do here. Add these signals, the blocks to my model, and gear. Throttle in, I'm calling it, and that's brake in. So I can also define not only a scalar value as an input, but also arrays, so with a dimension here. Okay, that's all. Unfortunately, we need also a terminator here for the open ports, so I don't need them because I have a scalar value. I don't need the rows and column. So I will need to add them here and add them also for the other part. Connect them. Okay, good. So this is now done. Next thing would be getting the outputs here and replacing this guy here by outputs. So next thing would be the gear out Yeah, and then engine RPM out, I would call it. But it's up to you how you call this for sure. Or just RPM out. I'm a lazy guy. RPM out. And then vehicle speed. Speed out. Okay, so we have set up our model for the inputs and outputs. We will see these outputs, inputs and outputs later on in CANape. I will show you. But there's also some other steps to be done here. So I need to go to the model configuration and, very important, get the solvers. So we need a fixed step solver. We need inline parameters. And very important, we need the right target. So the CANape comes, or our MATLAB add-on comes with a target, a TLC file. That's the cnp.tlc, and that's all I have to do now. So here are some more code generation options for setting up the options in here. So specify specific for CANape. Okay. In the next step, I would like to show you how to create these parameters. So we need to go to, that's all, MathWorks style, data object wizard, and find all my parameters and signals here in here. So as you can see, I have the signal, Simulink signals, and I have the Simulink parameters. So I will create them all. Create. So as you can see, the workspace has changed. Okay, and then last but not least, open the Model Explorer and go to my base workspace and switch these the storage class of these generated objects to exported global. It's all described in a help file. What are the necessary steps in here? If for sure, you can also script this. We provide also MATLAB scripts that this can be automated. But I just wanted to show you this. Okay, and then we're done. We can create the DLL. Here's I press the build button. So let's see if everything goes right here in here. So we will create an A12 file at the same time. We will create a model description file for the model representation in CANape. And here you can see also, here's the A12 file generated. So then all the files are generated in here. You see XCP basic, so that's the XCP driver, which is integrated in the DLL. And last but not least, we have a new DLL in here, which is called the same name as the model. So that was all. And let's jump then to CANape. And I will close that one. And I prepared a little demo already, or I prepared a small project already, so that we can do not lose time for this. So as you have seen in my animation at the beginning of this demo, I want to use a real ECU, use the CAN data, which comes from the ECU, and process it with my MATLAB Simulink DLL. So here's the project I created, and this is a very simple project. It just uses the data from CAN. So here, when it's open, here's a trace window. So when I start the measurement, I see data coming over CAN. So I want to use this CAN data. So I need to find the signal which provides the slider, and this is called ANI1. AN1 here. Add this to a graphic window, and AN12. AN12. That's the break. So that these are the two CAN signals I want to use here with my MATLAB Simulink model. So let's put them here on top of the window so that we can see it. So and then next step would be, so I have some input signals, and then how I want to process this with the DLL. And this is very simple. So we created a DLL, and let's jump to the location where we created this DLL. And this one is in here in the build. There's a build folder called CNP RTW. And here's the release folder, and there's a DLL. And just drag and drop this DLL to CANape, and then I can have the choice between creating an online model, so it processes online data, or I can also use it offline, as I said. Okay, let's create a new online model. As you can see here now, these are the inputs and outputs I have defined in Simulink. And now it's very easy to assign them to anything I have in my CANape configuration. Can be an XCP signal, can be an analog signal, can be CAN, FlexRay, Ethernet, some IP, whatever you have in CANape. So in this case, I have only CAN. So I can just drag and drop these to one. Where is it? Oops. Here to my throttle, and then I use this one for my brake. Okay, and then I have to decide, okay, what are my outputs? And the easiest one is just use it as a result. Okay, let's go here, and my two input signals. Okay, so I've them assigned in here. So that's all I have to do, and let's do the demonstration now. So I can visualize this data in another window. So under my measurement list, there's an algorithm section, and there's a MATLAB Simulink model section. So I can use this model and just drag and drop it to another window. So the algorithm designer, as you can see in the window, was open, but I want to see the values also here in a signal or a time correlated way. And oops, sorry for that. So I have a touchpad, which is kind of not so easy. Okay, but so let's start a simulation. Not a simulation. We really start a measurement now. We're taking the signals from the CAN and process it in the A12 file, the DLL file or the model, and here's the output of this one. So when I start the slider, let's make this axis scaling a little bit better so that we can see what happens. So I will now, unfortunately can't see, but I will change the slider for the throttle input. As you can see, so now my engine RPM goes up, the gear is shifted, and the vehicle speed is going up for sure. Yeah. So I go down, and then push the brake button pedal, so my speed goes down, and engine RPM goes back. So that's based on real data from my ECU or from my CAN bus in this case, and doing all these things here. So that would be one part. Hope we have enough time. I want to show you real quick that we can also have access to the internal parameters. So I can create a device for this, and then it's really interesting because up to now the DLL or the model is just a black box for us. But if I create a device based on this model, and I just have to select the A12 file which I have created. Where is it? Here is it. So I have an A12 file, and then go. They need the map file that was created. So that's also in here, in my RTW. Sorry for being very fast. I think we're running out of time. So I need to add a map reader for this. This was created by Visual Studio. So it updates the addresses. And that's all. So we have now, or I have now created a device which you can see in here. And now I have also, again, full access to the model internals. So here's the engine torque, and here's the EMAP. Maybe you know from the first one. So I can change this guy in here very easily. So yeah, it's getting crowded here, the space. But I just want to show you. So this is the normal signal. If I change my map here, let's say I switch them all to 0 somehow, and then run the simulation again. So I changed my model, my internal parameters of the model, and it's now I can step on the throttle. Nothing happens anymore because I messed it up here in my EMAP array. So, but I can, I hope you can see that there's a very easy way to change these internal parameters of the DLL and of the model without generating code over and over again. So you can use the same model. You can even share it to your colleagues, and they can use it, and they can do everything without MathWorks or MATLAB. Okay. Thanks for listening. I'm going back to my colleague and talk to you soon.
Okay, let's have a fast look on the slides again. So very quick, what are the advantages of this DLL generation? So we can add to our model or to our algorithm real measured ECU signals. And we can run the model and test the model with real ECU signals. We can do this online and offline, you have seen. And I think a very interesting topic is you need no MATLAB Simulink license to run this DLL. So your colleague needs a DLL or needs a license, creates a DLL and sends you then the DLL, the A2L and the link map file, and you only need then a CANape license to run this on your PC. So that means this model can be used then by multiple engineers at the same time on different PCs with CANape licenses. The model can be measured and calibrated like you have seen before in step 1. The same thing with the DLL. And very important, it's no rebuild of the model necessary. You just have the DLL. You can modify the DLL by modifying the parameters. And so you can do some tests, or you can do the first initial parameterization of your model very easy and very fast. Okay, so let's go to the next step. The topic is bypassing. What is bypassing? What does bypassing means? So we are talking about software in the loop, hardware in the loop, and we are running on target platforms. That means the model is tested on real-time hardware and or the target ECU. We have fast modification of the ECU algorithm, but we don't want to replace the complete ECU software. So because the generation, the integration of new software components in the maybe an AutoSAR stack needs many time, and it can be done faster by only replacing the needed software components. And we are working very often on hills, or on test benches, or on real cars to do these verifications of our models. And the goal is to do the final parameter calibration and the variant parameterization I told you before in the startup of this webinar. We are using the same DLL, or we can use the same DLL we have created before, and now we can run this DLL not on our PC like we have seen before. So we can run this DLL on a special hardware. It's our VN8900 hardware. It's a high-end hardware interface with a real-time PC inside, and the complete configuration of this model running on the DLL will be done in CANape, but the model execution will be complete done on the external hardware. So we save many resources, and we have more calculation power than on our PCs. We have no interrupts like a typical Windows PC offers us, well, all the time. Yeah. And so we can use the CANape vSignalyzer Target DLL. additional as a bypass or full pass solution. That means we create out of the part of the software part we want to exchange a DLL, and only this part should be then simulated on this platform, and the rest of the model or the rest of the ECU is a real ECU. So let's why we are doing this. So we want to reuse CANape project configurations. We want to have one tool to work from step 1 to step 3, and we want to use the same configuration from the first step to the final step in the model development. Motivation for bypassing. So I told you a little bit before, so the fast modification of ECU algorithms or code segments is the goal, but we don't want to replace the complete ECU software in the ECU. Maybe we only want to replace or test a part of this software running on the ECU. And we don't want to flash the complete ECU. It needs time. We have only a fixed number of flash cycles available on our ECU and so on. The existing ECU hardware could have insufficient RAM or flash ROM or CPU speed to run our next generation model. So how to test it? We have only the old hardware, and we have a new software component. Now we want to test it. So it's not possible to run this hardware component, this software component on this hardware, but we can do this with the bypassing technology we see now in some seconds. So with this, it's possible to test a new application, and we want to have the possibility to switch between the original ECU application, which is running on the ECU, and the new algorithm. That means the model which is running on our real-time hardware, or maybe on the PC, but better it runs on the real-time hardware. And we want to compare both under real conditions. The bypass execution could be done on the PC or on the real-time VN8900 hardware. So we have an extreme high-end access to our ECU with our VX1000 solution, so that we have no problems to get many data in quick times out of the ECU and write this data back on the ECU. We have the possibility with CANape and with this VX1000 solution to read out data we need for our model. So we can see this now in this very quick video solution. That means we have our model. Normally the model is using this software component, and now you can see in this video. I will start it again. So we are using CANape to read out these signals, which are normally going inside the model. We are run our DLL on our hardware platform, and we're writing back the result to our original target platform. That means we are bypassing this software component on the real hardware with this DLL running on the PC or the real-time hardware. And this could be a very fine and easy way to do some tests. Okay, for this we have prepared a small demonstration package too. So let's switch to my colleague Beck.
Okay. So I want to show you now bypassing in my last demonstration for today. And so we've seen the evolution from the model only to the target with real data. And now we see the same model also with bypassing. And what we have done here is I have the same model in here, and I have integrated this model into an ECU. in this case, I use a simulated ECU. This was easier to create. We have this XCP Sim, you might know already. So we adapted the XCP Sim, which is very easy to adapt. For sure, I had also the chance here to use a real ECU, but I don't want to reflash it during the WebEx. So I use a simulated ECU. Put the model in here, so the model, the application is running in the ECU, but a part of the model, and as you know, there was an engine subsystem. I want to bypass this engine subsystem in CANape or on the VN8900. So as we already have seen from this part, we create a DLL also with an XCP driver. We create all the other files which are necessary, like the A2L file or the map file. And then, when I have these files, I can put them into CANape, add them as a new file, and let them run with CANape. And then I'm able to do DAC and STIM or do the bypassing. So the application is still running in here, but one part of the application, in this case the engine subsystem, is running in CANape. So let's do this in a demonstration in here. So let's go here. So we need to find my I have a project here. So I start my simulator. So maybe you notice that's an XCP Sim simulator. It simulates an XCP ECU, and this one is connected through Ethernet, in this case with an UDP, and it's listening on port 5555. So that's all. So it's running. So I need to connect now with CANape, and let's start a project which I also created before. What is still running? Let's see. No. Okay. So let's go to start CANape with this project, with this bypassing project. So I have a VN8900 also here on my desk, the real-time platform. I first use it, let the PC run the DLL, and then I switch to the VN8900, and I want to show you this, how easy this actually is. So, but let's explain the configurations real quick, and then start the bypassing. Sorry for that. So that's a simulator. I need to restart it again. Okay, go online. Okay, so I'm online. So here are my models, or you already know these models. This is running in the ECU, and this is the bypass subsystem which is running on my PC or on VN8900 later on. So we have an engine torque map here, as we know already. So this one I can calibrate also during the bypassing. So to change the outputs of, or in this case, one output of my bypass. So I get two signals into my bypass. These are delivered through XCP into my bypass. It's calculated, and then it's outputted back to the ECU with the STIM simulation to the ECU. So let's go in here. Here's the same visualization of how it works. Here's my engine bypass, and let's start now. Let's see what is. Sorry, I switched to PC. So it's now running on the PC. So let's start the bypass. And as you can see here, my two inputs, and this one is the output. And in addition, so I see the output. In addition, here down there, I see the step time, which is also nice because, as you might know, bypassing is a very time-critical thing. The path here, we call this round-trip time, from getting the data to the DLL, writing it back to the ECU. That's the critical path. There are limitations. You cannot do this forever or too slow. Otherwise, the application will not run correctly. So there's a high demand for real-time applications. So we are running currently on a PC, and as you know, real-time on a PC is not really real-time. So we will have some spikes in here and things. So that's what we see in here is the model step time. Let's create a thing. So we see, the model step time. So how fast this is calculated is about 19 microseconds. So this is usually not very does not take very long to calculate, but the path here to get the data and stimulate it back, this is very dependent on the physical layer. Is it Ethernet? Is it just CAN? We would not recommend to do this on CAN. You need a very fast access to the ECU in this, as we said already, with the VX solution. So this means, so when we go here, you see that we are running on the PC right now. So, and I can really switch very quickly to the VN8900. When I change this button here, or this drop-down box, you see that this has switched to the VN8900. And the next time I run it, it's executing, and you can trust me, I cannot visualize it, but this is now executing on the VN8900 with better real-time abilities. So it's faster. We have a comparison in here. So the red one is a reference we did with a PC, and the green one is the actual thing. So you see this on one view. That's the red one is the PC, and you see very high spikes here and slower also. When we click on this one, it's about 80 microseconds at the peak here. And this one, the green one, that's faster, and also, but what is more important is the jitter or the delay based on the real-time system. How much is the delay? Windows just does some tasks, and this will delay the execution of the model. So this is a good example to show you. The bypassing, you can start on the PC, but if you want to have a real-time environment, moving to the VN8900 is I think recommended in here. So, okay, thank you for that. I will switch back to my colleague.
Okay, so the same as before. So just a few and fast overview about what we have seen in the last minutes. So the advantages of this technology is if you are using the VN8900, we have a real-time bypassing platform with extreme high or with extreme small jitter and latency times, especially if you're using our extension. So because we can use the VN8900 in two different modes, I call it normal mode, and additionally we have the possibility to set the VN8911, 12A, and 14 to an extended real-time mode. This is a special new mode which is available to get smaller jitter and latency times than if we have if we run it only on the normal VN8900. So, and additional and big advantage is that you can measure and calibrate this bypass DLL like a normal ECU, independent if it's running on the VN8900 or the PC. And this is very nice too. The bypass can be run standalone on the VN8900. So it's not necessary to connect the VN8900 to your PC. So you can connect the VN8900 maybe with the VX1000 to your ECU, put it in the car, and it runs completely independent standalone on the VN8900. Okay, good. let's come to the last part, the summary. So the question was at the beginning, is MATLAB, Simulink, and CANape a perfect team for model-based software development? I think we can say yes. So you have seen the theoretical part and the very nice demonstrations of Gernot in the last minutes. And so we have solutions for different use cases. For the early development phase, you can use the Simulink XCP Server to get XCP access directly in MATLAB Simulink. Later, you can create out with the Simulink coder and CANape and vSignalyzer Target DLL for run this DLL on the PC or on the VN8000 for online and offline use cases. Additional, if you later create with the embedded code or code for your target platform, it's completely easy to measure this ECU. This is our normal business, and we can use the same CANape model from the Simulink XCP server over the DLL back to the target ECU. We can always use the same CANape project. We have the possibility to use the Model Explorer to view the models on the different subsystems of the models in a graphical way directly in CANape. Very easy. Additional, we have some more connections between CANape and MATLAB. We have not shown in this webinar. Maybe you can use the CANape MC3 MATLAB interface. This is a possibility that MATLAB could act as a remote master for CANape. If this is necessary, the next step is we can export our parameters out of CANape to the MATLAB format. Maybe we have done the final parameterization of our ECU in CANape. Now we have a final data set, and we want to export these parameters to MATLAB, and then we can add this to our model. This is a use case of this. Additional, we can convert the M file to parameter files. This is the different or the other way. Okay, and one new thing in the last CANape versions, we have now the access to read and export the new MAT 7.3 file format, which is HDF5 based. We can read this in CANape, and we can write this format very easy. So there are some small preconditions to use this complete construct we have shown you. To use the MATLAB Simulink with the vector MATLAB Simulink MC add-on, it's all to create DLLs or to get the complete new blocks in your Simulink library. You have to install this MC add-on. This is available on our homepage or will be delivered with every CANape installation on our DVD we are sending to you. To create the CANape and vSignalyzer target, it's necessary that you have installed or the license for the Simulink coder on your MATLAB Simulink machine. This is important. And if you want to run the Simulink XCP server, you need an additional CANape option. It's called CANape option Simulink XCP server. And with the CANape MC3 MATLAB interface, it's possible within MATLAB scripts to access to all data sources inside of CANape. Okay, if you need help to all these topics, so this was just a very fast overview we have shown you today about this very interesting topic. You can always get in touch with our support. We have here our support hotline you can use, or you can send an email to our support colleagues, or you can use the competence of our training center. You can ask there to get a special training, or if you're interested in getting started, so please contact us. so it's always possible to get a more personalized session with you to help you to start up with these technologies. So from my side, thank you very much for joining this webinar, and I hope you have learned something in this webinar. Thanks to my colleague for presenting the very nice demonstrations. And let's have a look on the Q&A section if there are some questions.